Okay, welcome back. It is part 2 of day 2 notes, types of reactions. And we are talking about the single replacement reaction. And this is the activity series of metals, which you should have copied at the end of the part 2. Part 1 of notes, day 2. You should have copied this into your note guide. So let's start up here. Refresh your memory that this is the list. The top of the list is the most powerful of the elements. The bottom part of the list is the least powerful, if you will. Carbon and hydrogen are added in there on this list just for comparison purposes, so you can see where they're at. Most reactive at the top, least reactive at the bottom. Okay. So how this works is like Super Science Babe talked about with the do you want to dance? Sure, I'll dance. It all is about what is the most reactive. The most reactive metal will replace any metal listed below it. So the most reactive metal, potassium, on this list will replace every other element. It has the power to kick it out and then take its place. Okay. Let's talk about the double replacement reactions, also known as double displacement.
Alright, so we're going to talk about double replacement reactions, also known as double displacement reactions. This is an exchange of ions between two compounds. Typically what's produced is what we call a precipitate. That's a solid within an aqueous solution or a liquid solution. We'll actually get a picture of what that looks like soon. Alright, so here's a skeletal equation of what a double replacement reaction looks like. We have AX, and this happens in ionic compounds. So we have AX, and we know that A is a metal, and X is a nonmetal, plus BY. Again, B is the metal, Y is the nonmetal. Don't forget, metals always come first in ionic equations. So they're going to actually change up partners, okay? So metals don't want to be with metals, and nonmetals don't want to be with nonmetals. So we're actually going to, they're actually going to switch partners and switch them completely. So the A is now not going to be with X anymore. It's now going to be with Y. And the B is not going to be with Y anymore. It's now going to be with X. Okay, an easy way to remember this is the outside ions are going to come together, and the inside ions are now going to come together. But don't forget, metals will always, always, always come first. Okay, do not ever write the nonmetal first. So in this case, what's going to happen is Y is going to be a product. A is a metal, don't forget, and Y is our nonmetal, plus BX. B is our metal, X is our nonmetal. Don't get that mixed up. That can actually get you into trouble. Okay? So this is a good example of a skeletal example of a displacement reaction, or double displacement reaction. So let's look at an actual double displacement reaction. We have two ionic compounds that come together, aluminum carbonate and potassium oxide. And what they're going to do is the metal is now going to bond with this nonmetal, and this metal is going to go with that nonmetal. Polyatomic ions are going to act as nonmetals. Okay, so we have these subscripts at the bottom, 2, 3, and this 2. We're actually going to ignore them for now. Do not use those as when you're actually making your products. Just ignore them. We'll deal with them when we balance the equation. Okay, so we're just going to deal with the metal. The aluminum itself is going to bond with the oxygen. Okay, so how do they come together? Well, aluminum makes a +3 ion, oxygen makes a -2, cross those, make it even, and we come up with a new product, Al2O3. Okay, and now potassium is going to bond with carbonate. Carbonate is CO3, that is carbonate, so we're going to actually keep that within the compound. So we have K, which is going to make a plus ion, and sorry about that, carbonate, which is a -2 charge. We're going to cross those, and we're going to get K2CO3. Okay, and these are our products. And so now we have to balance it to make sure that the elements are the same on both sides. So we're going to just do that. And I'm just going to change that just for room's sake. Okay. So let's start with aluminum. We have 2 aluminum on the reactant side, 2 on the product side, so that's okay. Let's talk about carbonates. We have 1 on the, actually I have 3, I didn't copy that correctly. We have 3 on the reactant side. We're going to put 3 on the product side. That means we have 6 potassiums. We're going to make 6 potassiums, so we're going to put 3 here. And that means we have 3 oxygens. We have 3 oxygens. This is completely balanced. This is an overall double replacement reaction. Now, we actually can take this a step further and do net ionic equations. That's right. Those are actually the next step in dealing with double displacement reactions. But that's going to be shown in another video. Okay, so let's actually see this in action. We said that a precipitate occurs, so we're actually going to see what a precipitate looks like. So let's do that.
We're going to do a double replacement reaction with potassium chromate and silver nitrate. Here's my potassium chromate, and I see that when I add silver nitrate to it, I am forming a nice red precipitate. And the precipitate is silver chromate. It's a double replacement reaction. We are going to mix potassium iodide and lead nitrate, lead 2 nitrate. So I've got my lead nitrate in here, and I'm going to add some potassium iodide to it, and we're going to see right away that we get a precipitate of lead iodide. I'm not sure if you see this, but what a pretty precipitate.
Alright, so the 2 reactions that you saw are written up here on the board. Notice the silver chromate is the precipitate. Notice I wrote that as a solid as its state of matter. And down here we have the second reaction. It has the yellow precipitate, the lead. Notice again I wrote that as a solid. PPT you might see frequently. That just indicates that it's a precipitate. And those are very, very common examples of what a double replacement reaction is.
So, a double replacement reaction is an exchange of positive ions between the 2 compounds. Now, remember, we used the crisscross applesauce method. That's where you figure out the oxidation number of the anions and cations, and then you crisscross, and that will tell you how many of each you need. So here we have an example, Na2S plus CdNO3. You have a double replacement reaction, and that is where the Cd swaps with the Na. Okay? And then the last reaction type is called the combustion reaction.
Alright, so we're going to talk about combustion reactions. Combustion reactions are when oxygen combines with a substance and releases energy in the form of light and heat. Combustion reactions are a classic one, the very most exothermic reaction we can have. Exothermic indicating that it releases energy in the form of light and heat. That means exothermic. So let's look at this reaction. Alright, so we have hydrogen combining with oxygen to form water. Now that fact that it's combining with oxygen is our indicator that this is a combustion reaction. But then we also look at it and say, it only gives us one product. We can also say, oh, this is also a synthesis reaction. So this reaction actually falls under 2 different types of categories, combustion and synthesis. But typically, you'll see a combustion reaction with a hydrocarbon reacting with oxygen rather than other things. What is a hydrocarbon? Well, a hydrocarbon is a carbon-containing compound with hydrogens or oxygens attached to it. Let's look at this one below. So we have methane, or CH4, reacts with oxygen, which is our indicator that it's a combustion reaction. It's going to require a bit of energy for this reaction to take place, but it's going to release a lot more energy than it needs, indicating it's an exothermic reaction. Our products will always, without a doubt, always be carbon dioxide and water if the reaction is a complete reaction, meaning we put in enough energy for this reaction to take place fully. If we didn't put in enough energy, the reaction will still take place, but it won't be quite as nice. It will give us the products of carbon monoxide, not very good, very poisonous actually, and water. That's an indicator that it's an incomplete combustion reaction. Alright, so combustion reactions are always fun to watch. So let's actually look over here and watch a video on a combustion reaction in action.
Hey, here are one of these water bottles. So that's what this is, a water bottle. You're a big, strong man. I want you just to push on the sides there and see if that bottle will crush.
Oh, no.
It's hard, isn't it?
I
Right?
mean, I'm, you know,
You're there.
I'm
I
pretty
can
muscular,
tell.
but not even I am going to be
There
crushing
you
that
go.
side.
All right, so here's what we're going to do. We're going to let air do this for us. So put on your safety glasses because you get to now deal with not only fire but a flammable liquid. So we say fire. Try this at home, all right? So I have a flammable liquid here. It's actually ethanol.
Another
and that
suit
goes
down the
inside.
hole.
Nah, it's fine. You've gotten a refund on a lot of them. Now watch what I'm going to do is I'm going to spin this around so that we can get it to evaporate inside. So in just a second here, we're going to light this on fire. We're going to create some heat that's inside, and as soon as that heat is inside, it's going to push all those air molecules out. And then we're going to make a kind of a one-way valve. I'm going to put my hand on top of it like this, and we're going to see whether or not the air pushing around us, you can see the effects on this bottle. Fair enough?
Fair
All right,
enough.
so here we go. So a little match here. Do you want to, here, you do the honors, ready? So you're just going to drop it down inside.
Put your hand on
Yeah,
it.
I just going to drop it down inside. Yeah. Nice. Hear that? Now watch. I'm going to cover. Watch. You're actually crushing the bottle. Now I'm not doing that. Look, the air all around us is crushing the bottle. Listen to this. Listen. Isn't that amazing? So
That
it's that
is
air
very
pushing around it.
cool.
Now we get a
I'm
double
not kidding.
whammy.
That's
a strong bottle.
very
isn't
rigid
it?
plastic. Yeah.
Now look, watch this. Because we had combustion inside, this whoosh bottle, so to speak, what we're left with now is water. So when we pour this out here, this is
the
moisture.
byproduct of the combustion is water.
Exactly, it's carbon dioxide and water.
Oh,
So it's a bunch of great demos all in one.
All right, so what exactly happened in that video? Okay, so the guy had ethanol in an aqueous solution, and he put it inside that big container. Okay, ethanol's compound looks like this, C2H5OH. It reacted with oxygen, which is the source of the flame, so he put a flame in there, and that's our source of oxygen gas, and it reacted. Okay, and it gave us carbon dioxide as a gas, so all that oxygen was eaten up and gone away, and now we have carbon dioxide left, and we have water, as you saw him pouring out the water in liquid form out of the container. So why did it crush? Well, you look at it and you say, okay, we have for every, in the product reactant side, we have 3 particles of oxygen gas for every 2 particles of carbon dioxide gas. So we're actually losing some gas in this reaction. All these guys are eaten up, these are going to go away, and only 2 gas particles are going to be produced in its place. So that means we have less gas particles, and so the volume is actually much smaller, which is the reason why it crushed down. And then at the end, we also saw him pour out the water to prove that there was water byproduct. All right, so that is combustion reactions.
All right, so combustion reaction. Element or a compound reacts with oxygen, often producing energy in the form of light and heat. Often the other reactant besides oxygen is a hydrocarbon composed of hydrogen and carbon. Okay, here's an example of a combustion reaction. 2C8H18 plus 25O2 produces 16CO2, which is that carbon dioxide, and 18H2O, which is water.